everyone. My name's Roger Davies, and I'm the president of the European Astronomical Society. The meeting has already started this morning, and we've already had some good sessions. I'm very much looking forward to the rest of our second online meeting. But before I make some opening remarks, let me hand over to Alexandra Schouten from the local organizers, who's got some practical details and a welcome from Leiden. Alexandra.
A warm welcome from Leiden Observatory to all. My name is Alexandra Schouten and I am the host coordinator of EAS 2021, as I also was last year. I also guide the amazing team of 55 volunteers registered and many more who will support the sessions as technical hosts. The volunteers also have built and will support the 4-day social evening program in Gathertown. Please check your email boxes for the invites to the career evening, the student borrel, the pub quiz and games night and the music evening. All participants are invited and are also welcome to add to these events. Just remember, the social program is made for you and with you. EAS also invited Professor Sir Martin Rees to give a lecture to the general public on Thursday evening. This can be joined by anyone via YouTube stream and will be recorded. As to the conference platform, after a year of online meetings, you must be experts by now. But for any questions you might have, please check the emails by EES 2021 and take a regular look at the conference Slack channel. If you encounter technical difficulties, you can click on the little red man on that corner of your screen in the on-air platform. There is full support available and they are ready to help you. Last, I would like to remind you that by joining us on the EES 2021 conference platform, you agreed to adhere to the EES Code of Conduct, which basically says, be nice, show respect, and don't share content without the explicit consent of the author. This was all you need to know. Enjoy your time with us on the EES 2021 on-air platform and in Gathertown. I now would like to introduce you to Huub Röttgering. He is Director of Leiden Observatory and the local organizing committee chair.
Okay. Okay, thanks Alexandra, and thanks. Okay. So, thanks very much for attending this opening ceremony. And let me welcome you to Leiden. I fully realize that this is a virtual welcome to a virtual meeting. Locally, the good news is that as of this weekend, actually, the society is really opening up after almost 1.5 years of full and partial lockdowns. For many, and especially for the younger people, party time seems to be starting. It was clearly impossible to hold this meeting as a physical meeting, which is very regrettable, as it would have been so good to meet all of you in person. Leiden Observatory has a rich tradition and was home to many famous astronomers, including, for example, Oort and van der Hulst. It started in 1633 at the Academy building at the center of Leiden. See here a nice picture. In 1861, it moved to the old observatory next to the Hortus. See the slide here. Ending up at the science campus in the outskirts of Leiden. You here see the Oort building. With a large bachelor, master and PhD programs addressing many topics in astronomy and a very active outreach program, we are alive and kicking. An important partner is ESTEC at a 30-minute cycling distance. The biggest news probably is that ESRON, the Netherlands Organization for Space Research, is currently moving to the Leiden Science Campus. Many of you will know ESRON from its crucial roles in, for example, X-Men and Herschel, just to name 2 examples, and many more are coming. Here, picture 2 years ago, here the winter, and here the building now. It's ready. I would also like to welcome you on behalf of the entire Dutch astronomical community. Key players that are happily working together include ESRON, as just mentioned, Astron, who is taking care of the technical enterprise of radio astronomy, LOVAR, Schaye and so, and NOVA, the Netherlands Research School for Astronomy. NOVA is involved in building optical and infrared instrumentation and coordinates science of the 4 universities that have astronomy departments: Amsterdam, Groningen, Nijmegen and Leiden. Again, it would be so nice to see you in person in Leiden and show you around at this small university town with its many old houses, many museums and canals. And let me now take a slightly different angle. Here's a map of Leiden. And what's interesting is that many of the older houses that are decorated with text of poems, and poems of all kinds of languages. I'm not going to read up of them, but if you notice there are many. Here's another one. Here's another one. And there's also this Dutch poem by Jan Hanlo, which is fairly famous. And let me give you also the translation. There are haikus. Here is a beautiful one from almost 400 years ago. And of course, we as scientists also have poems. Here is a poem by Huygens, the famous equation for the pendulum. Here is Lorentz contraction. And interesting that the picture is taken with a train passing. And of course, Einstein's famous field equation. Here you can see it on the Museum Boerhaven. And there are also a few related to astronomy. And this is a picture close to the building of the old observatory that is depicting the Oort constants. And this is my final slide with a poem of someone 1,000 years ago from India. And blessed is the wise man who clearly knows the ways of all the universe, and happy likewise is the fool who never doubts his wisdom. Again, welcome, and let me hand over to the president of the EAS, Roger Davies. Roger, the floor is yours.
Thank you very much, Huub. It will be so nice to be in Leiden with you. This is the second time our annual meeting has been held virtually, and I'm delighted to say we have a record turnout. We've got over 2,400 registrations from 64 countries, over 1,000 oral presentations and over 1,000 posters. We're looking forward to 16 symposia, 33 special sessions, 5 lunch sessions, as well as the prize and plenary lectures. All these figures suggest that this has been a huge enterprise to organize. And for the second year running, the Leiden team, ably and abetted by the wider Netherlands community, have hosted us. I'm enormously grateful to them, and to the scientific organizing committee co-chaired by Joop, Schaye and Connie Arts, as well as my colleagues on the council, supported by the staff of the Cooni Congress, for their efforts to make the virtual EAS 2021 a success. The individual session chairs and their organizing committees have worked hard to produce an exciting program, each of which adds to the scientific vitality of this week's events. Astronomy continues to be very much in the news, and public awareness of the night sky is growing, which we hope to enhance through this meeting, specifically with the public lecture by Martin Rees on Thursday evening that Alexandra already referred to. Your society continues to work hard for you, and recently we made a successful application to the Wilhelm and Elsa Herreus Foundation to fund a series of workshops to promote the careers of young scientists from European research and academic institutions. These 5-day workshops will give participants the chance to present their own research, discuss their science, visit the local host institute, and have review lectures from senior astronomers. A pilot workshop will be held next year, and if successful, we plan to have 2 further workshops. I'm very grateful to the Herreus Foundation, whose focus is to support scientific research and education in physics, for funding this initiative. In March 2019, which does seem a very long time ago now, in partnership with the European Space Agency, the Society organized the first week-long exhibition and afternoon of talks at the European Parliament as an opportunity for parliamentarians and their staff to keep abreast of developments in astronomy. This was a very welcome and successful initiative, and the focus that week was on results from the Gaia mission. After a considerable effort, I'm pleased to say that a second event focused on exoplanets and involving both ESA and ESO with the Society is planned for the week of October the 24th, with presentations on the 26th of October, including one from the Nobel laureate, Professor Michel Mayor. Which brings me neatly to the 2020 Nobel Prize in Physics. It's a pleasure to congratulate a former Tycho Brahe Prize winner, Reinhard Genzel, my Oxford colleague, Roger Penrose, and Andrea Getz. It is surely a sign of the health and vitality of our subject that 3 of the last four Nobel Prizes in physics have been awarded for astrophysical investigations. The Astronet activity, coordinated by funding agencies across Europe, is reaching its concluding stages. On the 11th of June, the Society hosted an online event at which the panel reports were presented to the community as part of their consultation exercise. The Astronet roadmaps have set the future direction of large-scale infrastructures for astronomy, and a further consultation will take place at the end of July, when reports from the cross-cutting panels are available. And I'd strongly encourage all of you to engage with that exercise and participate. The Society continues to be grateful to all our organizational members. They play an important role in securing the financial sustainability of the Society and supporting the activities that we undertake on behalf of European astronomy. And I'm delighted to welcome 3 new organizational members this year: the Czech Astronomical Society, the Institute for Astronomy und Astrophysik in Tübingen, and the Astronomy and Astrophysics Journal. I'd invite any institution that's interested in joining as an organizational member to contact me or the treasurer. We hope to be back to a face-to-face meeting next year in Valencia, Spain. And for more information about the Society, members can attend the General Assembly at 3:15 on Wednesday. I encourage all of you, and especially the early career researchers, to join the over 4,000 of us who are now members of the European Astronomical Society, either through your national society or directly through the website. I wish you a stimulating, enjoyable, and most of all, a safe week. It's now my pleasure to introduce to you the editor-in-chief of the Astronomy and Astrophysics Journal, Thierry Forveille, and the chair of the board of directors, André Moitinho, to announce the winners of the first Astronomy and Astrophysics Awards for the Best PhD and Early Career Award. Over to you, André.
Thank you very much, Roger. I will share my screen. I have just here a couple of slides I would like to show. I hope you can see my screen. Can you confirm this, that you can see a slide? Yes. Okay, so, well, first of all, Roger, thank you. And I wish to thank the EAS for hosting the announcement of the A&A Awards in the annual meeting. It's really an honor to celebrate them in this extraordinary event, which is a reference in European and now even worldwide astronomy. On my side, I have a deep personal affective relation with the EAS meeting since I was a chair 11 years ago in 2010 edition in Lisbon. And I know it's a really complex thing to organize, and even months after the meeting, I would still sometimes have dreams in which something would be going very wrong in the organization. So this makes me appreciate even more the very professional organization of the EAS meetings these days. Before moving on to the announcements, I will just leave a few words on where A&A came from and where it is today. For a more thorough presentation of this very interesting history of A&A, I would really recommend watching the documentary on the history of A&A in the YouTube channel, or even the short article in the EAS newsletter from March this year. So A&A started 52 years ago as an association of 5 European countries, and today, this time later, it has become a truly international journal. It is a consortium of sponsoring organizations from 27 countries worldwide in collaboration with ESO. And it's not only European anymore. And there are always explicit possibilities of membership of new countries to join in A&A, to become owners of A&A. So, and of course, there is the big advantage that A&A member countries do not pay page charges. Right now, well, A&A is a journal that has this motto, a journal run by astronomers for astronomers. And right now we are carrying out a project for thinking and adapting the journal to the needs of our changing times. One of the big efforts is being put in pursuing an open access future for A&A. We are close to finalize a report that will be sent for consideration by the sponsoring agencies. But we're also pursuing this, strengthening the services and empathy with the community. For that, we are pursuing practice, safeguarding the best practices for scientific reproducibility and ethics to promote diversity, equity, and fair practices that reflect the culture and values of the worldwide community of astronomers. And with this respect, I am pleased to let you know in advance to the formal publication, so this is very recent and still not formally published, that the A&A Board of Directors has approved a few days ago that the publication policy would be updated for supporting retroactive names changes. With this, A&A expresses its commitments in respecting the rights and identities of authors, reducing or removing barriers to the inclusion of author credit and inclusion of author credit. Finally, we also have the mission of contributing to educate and inspire the new generation of researchers who will be shaping astronomy for the decades to come. We organize a scientific writing school for young astronomers. Last year in 2020, it was in China. Next year, it's going to be in Portugal, in Lisbon. And the subject of our celebration today, which is also, we established the awards for the best PhD and early career work, which we are announcing and celebrating here at the annual EAS meeting. And with this, I hand on the word to the A&A Editor-in-Chief, Thierry Forveille, who will announce the award winners.
Okay, do you hear me? Okay, so the A&A Awards are attributed, one for a PhD work, are attributed for article published in A&A. The first one is for an article published in the course of a PhD thesis, and the second one is for somebody who's in the early years of a post-PhD career. The winner of the PhD award is Miriam Keppler, who did her undergraduate studies in Munich at Ludwig Maximilians University, then moved to Max Planck Institute in Heidelberg for graduate studies. She completed first a master's degree, which included an Erasmus year in Grenoble, and then went on to a PhD, which she defended last year. And she's now a postdoc in the same institute. She's best known for the paper which gets her the A&A award, which is the discovery of a protoplanet in a gap of a protoplanetary disk. This is the first such detection and something that planetary astronomers had been after for quite a while. Both protoplanetary disk and planets have been imaged for now over a decade, and gravitational interaction with an embedded planet has always been put forward as one of the leading explanations for the gaps that are observed in some of those protoplanetary disks. But until Miriam Keppler's 2018 paper, that was just a strong assumption. She closed that loop by finding an uncontroverted observational example of a planet in a gap, and therefore an unambiguous proof that the gap is due to a planet. She's since built on this work by characterizing disks both the PDS 70 disk, where she found this first example, and other disks through both ALMA and near-infrared high-contrast imaging, and also characterizing the young planets through near-infrared spectrophotometry. This is work that has a very broad scope for somebody who's just out of a PhD. And I'm very impressed by that work, and it bodes very well for her future career. The Early Career Award is awarded to Joanna Drazkowska and is also on planet formation in disks by coincidence. Joanna did undergraduate studies and a master's degree in Torun at Copernicus University, and then moved to the Institute for Theoretical Astronomy in Heidelberg for her PhD. Since then, she's moved on to postdoc positions, first in Zurich at the Institute for Computational Science, and now at Ludwig Maximilians University in Munich, where coincidentally, the first awardee started her career. As I said, her work is also on planet formation, but definitely on the theoretical side. And she develops models of the growth of the solid phase of protoplanetary disks from micron-sized dust grain to Earth-size and larger planets. The 2012 A&A article for which she receives the A&A Early Career Award is a milestone in that field, because it was the first that overcame the so-called fragmentation barrier or meter-size barrier, which all previous models of planet formation had encountered. The issue was that as solid body grow in size, they decouple from the gas and therefore acquire large relative velocities, which means they tend to fragment when through encounters. She showed that the so-called traffic jam effect, which is a local drop of the radial speed of the particles, which results from the radial drift of the solids, can locally enhance the solid gas density ratio to the point where planetesimals can form via a particle gas hydrodynamical effect, which is known as the streaming instability. This removes the previous barrier at 10 centimeter to a meter to growth. This was very much a trailblazing study. It has triggered many follow-up studies on mechanism for dust pileup, both by Joanna Drazkowska and collaborators and by others, and it's been extremely influential. I'm very impressed by this work, and I can only wish her that she will soon get a tenured position, which I actually thought that she already had before looking into her application. Miriam, if you want to say a few words.
Yeah, thank you very much for the nice words. I feel really excited and very honored to be considered for this wonderful award. So thank you very much to A&A for considering me for this prize. I would like to say that all the work during my PhD would not have been possible without the tremendous support, help and mentoring from my supervisors, Thomas Henning, Roy van Bockel and Miriam Benesti, to which I'm really extremely grateful for having guided me through all these years. So really, thank you very much. Now, looking back at the last years, I think one very important thing I have learned is that teamwork is a very essential element to reach a goal together. And I have been incredibly lucky to work together with really excellent people. So there have been many colleagues at MKA in the Sphere Consortium, but at many other places in the world that have really significantly contributed to the work on PDS 70. So I would really like to thank all of you for all your great support and efforts. And yeah, it was really a pleasure to work with you and also lots of fun. So thank you very much.
Joanna, your turn.
Thank you very much. I am honored to receive this award from the A&A. So first of all, I would like to thank the co-authors of the paper, Jan Alibert and Men Moore, and also the colleagues who have supported my application, Anders Johansson and Alessandro Morbidelli. So this is a very special moment to me to see this particular paper being recognized, because it was in fact the first paper on which I worked fully independently after finishing my PhD. And it was a very challenging project because no one has really explored similar questions before. So I really had nothing to compare to, and I didn't know if my results would make any sense. And of course, it all took much longer than I expected. So my message to the younger scientists here is to be brave and to tackle the very hard questions, and also don't get discouraged if things don't work on the first try, because in science they usually don't work. And if anyone wants to know more about my work, I invite you to visit my poster on this conference. Thank you very much.
Okay, I will take back the word. Well, thank you, Thierry. Thank you, Miriam and Joanna. You know, I already said what I had to say, but I just want to add something else, because one of the intentions of these awards was to inspire the younger generations. But, you know, just being here with you, I think it worked also the other way around. You really inspired me too. So thank you very much, and all the best. And I hope that we will meet again here next year. Thank you, Roger. Thank you to the EAS for hosting these awards.
Thank you, Andre. And congratulations to both the award winners. That's wonderful to see. So it's now my privilege to introduce the Zwicky lecture given by Professor Sir Martin Rees. It's the inaugural Zwicky Prize lecture. Martin Rees's career has been garlanded with awards and prizes, too numerous to mention all of them, but a few highlights are the Gold Medal of the Royal Astronomical Society in 1987, the Gruber Prize in 2001, the Crawford Prize in 2007. Martin is the Astronomer Royal for England, a former president of the UK Royal Society, and a former Master of Trinity College, Cambridge. He became a peer, Lord Rees of Ludlow, in 2005, and was admitted to the Order of Merit, a personal gift of the Queen, in 2007. The citation reads, Martin Rees is awarded the 2020 Fritz Zwicky Prize for Astrophysics and Cosmology for outstanding contributions, including seminal papers on active galaxies and black holes, the origin of gamma-ray bursts, the large-scale structure of the universe, and the cosmic microwave background. This exceptional, broad oeuvre has been both prescient and enormously influential. It gives me great pleasure to introduce Martin Rees to deliver the inaugural Zwicky Prize lecture. Martin.
Thank you, President, for these kind words. It's a great privilege to be the first winner of this award, and I thought it might be appropriate to start off by first making sure I can make my slides work. Yes, okay. And to offer some words about Fritz Zwicky, a great astronomer and a remarkable polymath. His most celebrated contributions date from 1934, when he wrote a paper with Walter Baade, in which he speculated that massive stars ended their lives when their cores collapsed to make neutron stars. releasing enough gravitational energy to power a supernova and to accelerate cosmic rays. And this was before supernovae were recognized as a distinctive phenomenon, and only 2 years after the neutron was discovered. In the following few years, he used the 18-inch Schmidt telescope at Palomar to systematically search for supernovae. And he also famously studied galaxies and clusters and inferred that there was dark matter in the Coma cluster, because he realized that the masses of their constituent galaxies didn't provide enough gravity to prevent the entire cluster from flying apart. Again, a prescient precursor of ideas that became well corroborated, but not for another 40 years. He also realized in 1937 that clusters of galaxies would act as gravitational lenses, magnifying distant background galaxies. Testing this was beyond the capability of telescopes in the 1930s, but of course it is now a well-established and well-studied field of the subject. And here's an example of some lensed streak-like background galaxies. Zwicky was highly inventive in diverse fields apart from astronomy. In particular, he worked on rocketry during World War II and wrote 30 papers on rocket propulsion. Indeed, it's not well known that he was the first person to send an object, which he called an artificial meteor, into orbit around the sun. In 1957, just 2 weeks after Sputnik 1, he launched an Aerobee rocket, having put a shaped charge into the nose cone. When the rocket reached a 100-mile altitude, the charge exploded, accelerating pellets up to well above what was needed to escape from the Earth. This may have been just a stunt, but it was an impressive one, deserving of newspaper headlines like this one. Often the most inventive scientists are impatient, not the same people who undertake long-term programs. But in his later career, Zwicky was a real Stakhanovite data gatherer. His atlas of galaxies and clusters, over 30,000 galaxies, filled 5 volumes. And he produced a separate catalogue of compact and disruptive galaxies, a key resource at that time, as it included many systems that are now realized to have active galactic nuclei. He is with these volumes in front of him, probably saying what he thinks of most of his senior colleagues. Zwicky died in 1974. And I luckily got to know him a bit in his last years. That's because as a postdoc, I made 2 extended visits to Caltech. And despite his proclivity for making enemies, he was very friendly to young scientists. At Caltech, in the Robinson lab, the astronomy professors all had offices on the top floor, except for Zwicky, who worked in the basement alongside his massive plate collection. And the only professor who engaged with him at all was Walt Sargent, who took spectra of many of the compact galaxies in his catalogue. But postdocs and graduate students also had their desks in the basement. And it was a real bonus that Zwicky would often wander in to chat with us, speaking his mind and reminiscing. I have fond memories of him, and it's a special pleasure to receive an award that commemorates such an extraordinary scientist. What would he make of today's astronomical community? He'd surely have admired its vibrancy, its internationalism, and the huge progress of recent decades. But I think he'd have berated us as individuals for having become over-specialized, too narrow in our interest for his taste. And he'd certainly himself have been unsuited, even allergic to the large teams that so many projects now require. He would envy, as a citizen of the world, he'd have applauded how Europe has fully matched the United States in astronomical projects, both on the ground and in space, via ESO and ESA. And he then beat today's computers, enabling the cataloging of millions of galaxies in deep fields and of 2 billion stars in the Gaia survey, enterprises far beyond unaided human efforts. And he'd been gratified that the case for dark matter is so strong. Simulations of how galaxies form and evolve, and here's one, only match the data if there's about 5 times as much mass in dark matter as in atoms. But it's disappointing, of course, that we don't know what the dark matter is, not by underground experiments, nor from the annihilation line, nor from LHC experiments. Many of us haven't given up hope. Some candidates have been ruled out, but there's a huge range of parameter space in which heavy neutral particles or axions or other exotica could be hiding. However, although Zwicky knew Einstein, a fellow Swiss, I guess he'd have been rather more receptive than most of us to radical alternatives that modify the laws of gravity. He died 25 years before we had another surprise, that the cosmic expansion was accelerating. He'd have been gratified that supernova observations were crucial to this discovery. The acceleration is seemingly driven by an energy and tension latent in empty space itself, what's often called dark energy. And explaining this is really daunting. Most ideas, string theory or loop quantum gravity, suggest that space itself has a grainy texture or microstructure, but this structure would be on the Planck scale, 10 to the minus 33 centimeters. This is a scale a billion times smaller than an atomic nucleus, where quantum theory and Einstein's theory meet. It's the size of a black hole whose Compton wavelength equals its radius. In string theory, each point in our three-dimensional space is actually an origami in 5 or 6 extra dimensions, wrapped up on the Planck scale. Theorists are tackling this challenge, but we shouldn't expect answers anytime soon. Indeed, the maths of string theory may be too hard for human brains to cope with. Perhaps AI can help by exploring the intricacies of this 10-dimensional geometry a billion times faster than humans. But the upside, however, is that a theory that could account for the dark energy, the microtextual space itself, might also yield insights into the very beginning of our universe, when everything was squeezed so dense that quantum fluctuations could, as it were, shake the entire cosmos. It's a huge triumph that we can trace cosmic history back to the first nanosecond. That's when the observable universe would have been compressed to the size of the solar system. A nanosecond is the stage when every particle has an energy about as high as can be generated by the LHC accelerator in Geneva. Before that, conditions are so extreme that we lose our foothold in experiment. But many believe that key features of our universe were determined far earlier, perhaps in a so-called inflationary phase, when the observable universe expanded from microscopic size to the size of an apple. And these are some of the key questions. First, what caused the fluctuations which were present in the early universe and which are the seeds for galaxy formation? Second, what does the universe, well, why does the universe expand as it does? And what determines the mix of things in the universe? Atoms, dark matter, and radiation. These are all questions that can't be settled without probing the ultra early universe. And incidentally, another fundamental question is, was our Big Bang the only one? Or does the physics imply there to be many, that we live in a multiverse? And our universe would then be a sort of archipelago. We'd be one Big Bang among many. Tackling these questions involves speculative and as yet untested fundamental physics. and will keep mathematicians busy for decades. But there's a separate strand of cosmology, which I call environmental cosmology. That's understanding how the universe evolved from its near homogeneous dense beginnings into the complex cosmos we see around us and are part of, and which allowed our emergence. Here we understand the relevant physics, but the situation becomes messy, especially when matter becomes clumpy and stars formed, as in a simulation. This is an enterprise that demands a different style of science from fundamental physics. In Werner Israel's metaphor, it's not chess, it's mud wrestling, but it's complex to model, just like our weather is. And progress in this requires ever more powerful simulations, but even more crucially, powerful telescopes so we can look back further into the past. And so here to remind ourselves is the set of massive instruments that are being brought into service now, JWST, hopefully later this year, ALMA, of course, already there, and the extremely large telescope, ELT, etc. All these hope to probe back towards first light when the universe lit up about 200 million years after the Big Bang. And the square kilometer array, incidentally, can in principle look back still further, using the 21 centimeter line to do tomography of the emerging filamentary structure which preceded the first stars. That's really exciting. But before leaving cosmology, I want to add a perhaps curmudgeonly remark, and I needn't apologize for that when commemorating Zwicky. Popular presentations of cosmology customarily present this pie diagram, according to which 5% of the universe is baryons, 25% dark matter, and 75% dark energy. This apportionment is, of course, true of the present-day universe, but it distorts the relative astrophysical importance of dark matter and dark energy. Dark matter is crucial both inside and outside galaxies, and was crucial in the past in determining how galaxies formed. In contrast, the dark energy, which has a density seemingly uniform in space and probably in time too, is everywhere swamped by dark matter for the first 5 billion years of cosmic history. So it had minimal influence on how cosmic structures were laid down. Moreover, it's swamped even today within galaxies and clusters. Dark energy is, as I indicated, the number one challenge for fundamental physics, but it's almost irrelevant for astrophysicists. Zwicky reveled in the complexity and variety of cosmic phenomena. Neutron stars, discovered more than 30 years after he first envisaged them as remnants of supernova, most famously are exemplified in the Crab Nebula, where there is in the inner parts a small neutron star spinning at 30 times per second. And neutron stars have ever since been the gift that goes on giving. They're valuable as probes of extreme physics, as precise cosmic clocks, as sources of gravitational waves, etc. And Ben Stappers' talk in this session will address a remarkably new phenomenon, fast radio bursts, FRBs. We don't quite know what they are, but they probably involve intense flares on the class of neutron stars with magnetic fields up to 1 trillion Teslas. But let me finish by mentioning what's perhaps been the most exciting astronomical developments of the last 20 years, opening up the rich and complex field of exoplanets. They're the theme of the first plenary lecture in this session, just after mine, by Laura Kreidberg. I won't encroach on her territory, except to remind everyone of the remarkable broad brush inference that we can already draw. We know that most stars are orbited by planets of some kind. And we also know that a very rough estimate is 1 in 6 have a Earth-like planet around them, a so-called habitable planet, which is at the distance from its parent star, such that water neither boils away nor stays frozen. These, of course, are habitable, but that doesn't mean they're inhabited. There's huge variety among planetary systems, as we'll hear in the next talk. But I want just to mention one, which is a especially remarkable one. This is called TRAPPIST-1. It's a miniature solar system. It's a nearby red dwarf star with 7 Earth-sized planets orbiting around it. A miniature solar system where each planet's year lasts between less than 2 days and about 3 weeks. Viewed from the surface of one of the planets, the others would loom larger than our moon does to us, swinging fast across the sky. The outer 3 are in the habitable zone in the sense that water can exist, but stellar flares would render them hostile abodes to life. And they're very unearthly for other reasons. They're probably tidally locked, so they present the same face to their star. One hemisphere in perpetual light, the other in perpetual dark. So were they inhabited by aliens, to be astronomers segregated in one half, everyone else in the other half? This system, by the way, was discovered by Michel Guillon and his colleagues using a 22-inch telescope. Zwicky would have cheered the fact that a small telescope can still make amazing discoveries. But the discovery was, of course, followed up by bigger instruments, including the Spitzer Space Telescope, which took this data, showing very clearly the dips, measuring the transits of these 7 planets. Well, could there be life on any of these planets? Here we're still in the realm of speculation. But unless the origin of life on Earth involved a rare fluke, I'd expect spectroscopic evidence of a biosphere on an exoplanet probably within 20 years. To analyze the light from an Earth-like exoplanet, rather than just its shadow in a transit, does require a really big telescope like the ELT with a high resolution spectrograph. You've got to take the spectrum of the star and the planets, and by separating out the part that changes with the planet's orbital phase, you can infer what the planet's spectrum is, perhaps with enough precision to look for evidence of oxygen, chlorophyll, something out of equilibrium. But I won't hold my breath for the discovery of aliens, although I think that SET is a worthwhile gamble, but that's another story. So just to conclude, when the history of science is written and covering recent decades, I think the amazing progress towards delineating the 13.8 billion years of cosmic evolution would be acclaimed as one of its greatest triumphs. Up there with plate tectonics, the genome, and the standard model of particle physics. And the future's bright. Some major fields in astronomy are just getting going. Exoplanet research is only 20 years old, and serious work in astrobiology is really only starting. So astronomers are going to have a wider variety of challenges and need a wider education. We need, especially in fields like exobiology, polymaths who revel in complexity. We need some young Zwickys, and let's hope there are some at this conference today who will seize these opportunities. So thank you for honoring me with this award, and thank you for listening today.
Thank you very much, Martin. I hope you can hear me. Can you hear me?
I can indeed, yes. And
Okay, and you can
I'll try and end the screen sharing, yes.
So here we are. Well, it's my pleasure to present you with this certificate, and one day I will.
Right. Well, thank you very much.
So here is the first Zwicky Prize award. You have demonstrated in your talk, Martin, what a wonderful polymath you yourself are, you know, Zwicky's chastising colleagues for being too specialized and looking down the wrong end of the telescope, perhaps, you know, is something that we all have to be careful about. Although I did notice that you were far more optimistic than, for example, the late Riccardo Giacconi about when we might get evidence of biological activity on another planet. If I remember correctly, his goal for astronomy in the 21st century was to understand the universe from the Big Bang to the origin of DNA, which is, I've always thought a wonderful aim, and certainly entirely one that Zwicky would embrace himself, I'm sure. So Martin, that was an absolutely tremendous, wide-ranging talk. Thank you so much. And it's my pleasure now to open the talk for questions. I don't know whether the moderators have got any ready. Have we got questions ready?
Currently, Roger, there's none, but there is a very thank you for a very nice talk by Isabel Santos. So at least I should also congratulate Martin Rees for this. So far, we're waiting for more questions.
Martin himself, I think.
Can I respond to Roger's comments, perhaps, and to Coney? I think obviously one thing we have to realize as astronomers is that everything in the world of biology is much more complicated than atoms or stars or anything else. So obviously that's the biggest challenge of all, far more complicated than understanding the weather or star formation. But it would be wonderful if you could find some evidence for a biosphere on any single planet. I think that would be wonderful. Of course, another point which I didn't mention is that if we find evidence for any kind of life elsewhere in our solar system, where we don't expect advanced life, but if under the ice of Europa or Enceladus we found evidence of life, that would be a really epoch-making discovery, which would rule out the possibility that life was a rare fluke. And if it had risen twice in one solar system, then that would tell us straight away that the galaxy must be teeming with life in a billion places. So that's why to look at even the simplest life in our solar system is very important. And if we say one other thing, to perhaps be slightly closer to what Giacconi might have thought, I would imagine that later this century, we will have the next but one generation of massive instruments beyond the ones that I showed in my slide. And perhaps these will include a huge space-based optical interferometer, which could actually get a resolved image of an exoplanet, not just seeing it as a faint point of light, a pale blue dot. And if that could be done, I would set the target as 2068, because that would be 100 years after the famous Earthrise image taken by Ed Anders on Apollo 7. And it would be wonderful if 100 years after that, we could have some sort of image of an Earth-like planet orbiting another star. So that would be a target.
That would be tremendously exciting and a good goal to aim for.
Right.
If there isn't another question, Mark, I could ask Martin. Go ahead.
The first one that I would mention is from Alexander Shulevsky. Dr. Rees mentions the need for polymath, and he's correct that they are crucial. However, do we think that our funding landscape allows for their emergence? If not, what needs to change?
Well, I think the situation differs in different countries. I mean, I'm in a country where the curriculum is much too specialized from the age of 16 onwards. You have to decide to do humanities or science, and then you have to decide whether to do biological sciences or physical sciences. And I think we need to broaden our education so that there are people who go into astrophysics with facility in physics, computing skills, and also some knowledge of chemistry, of course, and maybe one day biology. So I think we've got to incentivize that. And of course, the other point is that things are changing so fast that we can't depend on what we learn at university. We've got to have lifelong learning and catch-up courses of all kinds. And I think most of us who have been active in science realize we've learned far more since we left university than we ever did at university.
In fact, there's a lesson there, isn't there, a sort of counter to one of the points you made that Zwicky would promote, which is that in order to bring together this multidisciplinary range of ideas and concepts to attack this problem, you undoubtedly are going to need a large team of scientists with different training.
Oh, indeed.
So this is really going to be a big team project.
Oh, indeed, that's inevitable. And and I think actually, if you look at the history of our subjects, there are all these vendettas. I mean, Zwicky was famous, but there was Hoyle and Ryle and all these other people didn't get on. And I think the fact that our generation has fewer of these is not that we're of a sunnier disposition than our predecessors, but it's that we are more involved in collaborations. We realize we are often international. So I think this does mean that we can't be quite as vendetta prone as scientists were in the past.
No, can't afford to be. Mark.
There are a few more questions that are related, so I'll give a synthesis on the question of the best candidate on dark matter, your opinion on dark matter and dark energy, and also how SK will contribute to dark energy and dark matter.
Okay. Well, I mean, I think we've got to be open-minded. The point I'd make is that there are at least 10 powers of 10 between the highest energy particle, which could be detected by the underground experiments or created at the LHC. And we don't have physical models for it, but there's lots of parameter space where neutral heavy particles could be hiding, being almost indetectable. Because what we know from the simulations is that the dark matter has the properties of a swarm of collisionless particles, heavy, neutral with small cross sections. It doesn't matter what they are anywhere in that range. But of course, there are other ideas. There are ideas that they are tiny masses, or things like axions, or lots of other ideas. And of course, as I mentioned, there are some people who think that the dark matter's not there, or it's somehow linked to the dark energy in a complicated way. And this involves changing maybe even Newton's laws of gravity, as in the case of the Mond theory, or certainly changing Einstein's theory. And I think I mentioned Zwicky would probably have been very happy to do that sort of thing. But my personal betting is that we won't need to abandon Einstein or Newton, and we will discover that there is some kind of particle which can explain the dark matter. The dark energy, as I said, the data are all consistent with it being like Einstein's cosmological constant lambda being independent of time. We don't know how much it changes with time, if at all. What we do know is that it changes with time more slowly than the density of anything else, because it can't be important at high redshifts, because that would inhibit galaxy formation. So at the moment, everything's consistent with it being Einstein's lambda, and would tell us that empty space has some non-zero density for some reason, which we won't discover until we have these theories like string theory or loop quantum gravity.
Thank you very much, Martin. There certainly is much left to do, and you've given us a whirlwind tour, a wonderful lecture. Congratulations on the first Zwicky Prize. Thank you very much for your lecture. We look forward to seeing you again on Thursday evening.
Okay, thank you very much.
Thank you. So it's now for me to hand over the chair to the chairman of a scientific organizing committee. But before I do that, I just want to remind those listening in that there are 1,000 posters to look at. And there are also a big range of exhibitors that have things to look at on the on-air platform as well. So do make full use of the posters and the exhibitions. So now I'll hand over to Joop Schaye, who will chair the rest of this session. Thank you very much.
Thank you, Roger. It's a great honor to introduce Laura Kreidberg, our next speaker. Laura did her PhD at the University of Chicago in 2016. After that, she was a postdoctoral fellow at Harvard, where she actually had 3 prestigious fellowships at the same time. After that, pretty recently, she became one of the directors of the Max Planck Institute for Astronomy in Heidelberg, where she heads the APEX department. Laura works on observations of exoplanet atmospheres, and particularly space-based telescopes is what she uses. So she's been PI of many different observing programs with Spitzer HST and soon JWST. She's one of the people who pioneered the use of HST, Wide Field Camera 3, for exoplanetary transits. She's also authored software that is widely used to calculate exoplanet transits and phase curves. And very recently, she received the AnyJump Cannon Award from our friends at the American Astronomical Society. And today she will tell us about planets are places, characterization of other worlds in the 2020s. Laura.
Thank you very much for the kind introduction. It's my pleasure to be here to share some fun results from the field of exoplanet atmosphere characterization with you today. So let me just get my screen share going. All right, good. Can I get a thumbs up that you can see that?
Yeah, we see it.
Looks good. Okay, wonderful. Yeah, so it was, I really enjoyed hearing the discussion after Martin's talk about how soon we may be finding evidence for inhabited exoplanets, and I'll weigh in with my own take on that today. So first, I'll start with a very brief history of exoplanets. The field is very young. The first planet beyond the solar system was discovered just over 25 years ago. And since then, over 4,000 planets have been confirmed to orbit other stars. This figure that I'm showing on the right shows the number of planets as a function of their discovery year. And I always point out that this is not a cumulative distribution. This is just the number of planets discovered every year. So you can really see the acceleration in the rate of discovery. And we don't expect the stream of discoveries to stop anytime soon. There are a whole bunch of new and upcoming observatories that are searching for additional planets, in particular those that orbit some of the nearest and brightest stars that are the best targets for us to follow up and characterize in more detail. So boiling down all of those detections into a couple of statistics, I think the punchline is that planets likely outnumber stars in the galaxy. We know now that sun-like stars host at least 0.7 planets per star on average, and that's a lower limit because we haven't yet had time to explore for the smallest planets or longer orbital period planets. M-dwarfs, which are the most numerous type of star in the galaxy, host even more planets with an average of at least 2.5 or so planets per star. And as we heard earlier, the importance of this discovery was recognized by the Nobel Prize awarded to Didier Queloz and Michel Mayor. What have we learned from the planets that have been discovered so far? Well, I would say that if there's anything you can take away from this talk today, it's that exoplanets are much more diverse than the planets of the solar system. This figure shows planet mass as a function of distance from the host star in astronomical units. You'll see Earth towards the bottom center of the plot marked in black. And this figure has not been corrected for any kind of selection effect. So you'll see a big cluster of what we call hot Jupiters in the upper left. But what I want you to take away is a couple of different populations that are very interesting to us. One big one is a population of very hot planets. It turns out that it's very common for planets to orbit interior to the orbit of Mercury, some with orbital periods as short as 24 hours. There's also an abundant population of planets that are intermediate in size between the Earth and Neptune. Everyone is currently discussing what we should call these super Earths, mini Neptunes. I actually kind of like Neptini, but we really don't know. This is a place where atmospheric characterization can help us to distinguish whether these planets are more like scaled up Earths or scaled down Neptunes or something else entirely. There's a population of intermediate between planet and star type objects, and a whole host of things that I call oddballs, planets with very high orbital eccentricity, planets orbiting 2 stars or white dwarfs, super puff planets with densities as low as cotton candy. And there's also a whole part of this parameter space that we have not yet had the sensitivity or time to be able to explore. So we're really, in spite of all this progress, there's still really a lot of room to continue exploring. So now that we have started to find all of these planets and find systems that are nearby and close enough to characterize, this is a wonderful time to study the planets in more detail, and in particular to look at their atmospheres. And this is what I do in my own work. I'm interested in how planets form and evolve and what we can learn about those physical processes from their present day atmospheres. We also know that exoplanets are found in very extreme environments, like these very short orbital periods. And so what does that do to your atmospheric properties? How does that change your weather, your cloud formation, etc.? And of course, our huge question that I think we're all most interested in answering is whether we can infer the presence of life on another planet by studying its atmosphere. So this is a challenging prospect, and we have thrown everything but the kitchen sink at characterizing exoplanet atmospheres. I've listed a few of the primary workhorse facilities here on this slide. I don't have time to talk about all of them. I'll focus primarily today on results from Hubble and Spitzer. How do we actually characterize the atmosphere of an exoplanet? So this is a whole PhD thesis worth of science crammed into one slide. The very simple picture is that for a transiting planet, as it passes in front of its host star, the starlight will filter through the planet's atmosphere. It can get absorbed or scattered by atoms or molecules or cloud particles that are present there. And conversely, when the planet moves behind the star, any thermal emission or reflected light is blocked during the secondary eclipse. And so with these two types of observations, we're sensitive to the chemical composition of the atmosphere, what it's made out of, its temperature structure, its climate, and also whether the planet has clouds or haze. To make this a little bit more real, here's an image of the Earth taken from space. You can see the beautiful blue Rayleigh scattering signature with the moon in the background. If you move to the infrared, you'll note that that Rayleigh scattering signature goes away. So I'll just toggle back and forth. Oh, I don't know if I can go back. Ooh. There it is. Now it vanishes. But if you move a bit farther into the infrared, at 9.6 microns, there's an absorption band from ozone. And so you can see that the Earth appears a little bit bigger there. And this is exactly the effect that we are searching for on extrasolar planets. And I would be remiss if I didn't mention that this is an extremely challenging measurement to make. Here's an example of raw data from the Spitzer Space Telescope in the top panel. And you can see the data looks really messy. You might imagine there's a transit signature in the middle there, but there's all these jumps and wiggles and breaks. Thanks to very, very careful work on the part of many, many, many graduate students, it's possible to calibrate these data and correct for systematic noise from the instrument, and actually find signals due to the planet that are over an order of magnitude smaller than the systematic noise from the instrument. And I should emphasize that this is our very best case. So a feature amplitude of 0.1% is as easy as it can get. That's for a hot Jupiter with a big hot atmosphere that's as easy as possible to see. if we want to push to more Earth-like planets, that signal will go down by at least an order of magnitude and maybe 2. Exoplanet atmosphere characterization is also challenging from the modeling side. And the way I like to think about this is that the models have to cover an enormous dynamic range. So we care about physical effects happening on microphysical scales. So that would be things like cloud condensation. We care about planet-wide scales for atmospheric circulation, jet stream, things like that. And we also care about how the atmosphere evolves on short times, that's weather, and very long times, like how much of the atmosphere could escape over the lifetime of a planetary system. And so this, I would say that atmosphere characterization is equally as much of a challenge for the observers and for the modelers. Okay, so what I'd like to do in my talk is outline a couple of frontiers in exoplanet atmosphere characterization to give you a flavor of where we are today and where we will be going in the very near future. So the first one I'd like to talk about is using the present day composition of the atmosphere as a kind of fossil record for the conditions in which the planet formed. And I'm showing here a figure for the solar system planets showing how their atmospheric metallicity varies with planet mass. And I should emphasize that this is most relevant for gas giant planets that have maintained a primordial atmosphere that was left over from their initial formation conditions, not a secondary atmosphere that may have formed later during the planet's lifetime. So there's a well-known trend in the solar system that the smaller the planet is, the more enriched its atmosphere is in metals. A very basic question is, why is this? Is there something about the ice giants Uranus and Neptune that is preventing them from accreting a large amount of hydrogen and helium from the disk that would dilute their atmospheres? What happened to Jupiter that made it experience runaway gas accretion to dilute its atmospheric metallicity in contrast to the ice giants? We don't know for sure. But with a limited sample size from our own solar system, it's very difficult to say whether this pattern of atmospheric enrichment is universally true or whether it is simply an artifact of the small number statistics that we have from our own solar system. So I set out to measure the atmospheric metallicity for a hot gas giant. This is one of my favorite planets called WASP-43b. I nicknamed it Jalapeno because it's a hot Jupiter. The atmospheric temperature is about 1400 Kelvin. And so I measured a very precise thermal emission spectrum and transmission spectrum for this planet using wide field camera 3 on Hubble. You can see in the left-hand panels a clear signature of water absorption for both spectra. And I'll remind you that absorption is up in transmission spectroscopy because the atmosphere is more opaque where it is, the planet is larger where the atmosphere is more opaque. And together with Mike Lyon, we did a fit of these data to explore what possible atmospheric properties would match the data. And we found that the planet has to have a water volume mixing ratio of between 200 and 3,000 parts per million. And I know that that doesn't mean a lot to many of you in the audience. So let me put it in context here and show where WASP-43b Jalapeno falls on this plot that I showed from the solar system. And if you assume that the water abundance in the planet is representative of the overall metallicity, you find that WASP-43b lies beautifully in line with the solar system trend. So we found this result. We thought, this is wonderful. There's this exoplanet that even though it's presently in a very different location from Jupiter, it appears that its atmospheric composition is similar and perhaps its formation pathway was the same and it later migrated to its current location. I am an astronomer, so I'm happy to generalize from a small sample, but even for me, I think it's pushing it to generalize from a sample of 1. So what I usually say about this result is that it's a nice proof of concept that precise abundance measurements are possible for exoplanets. But I always said the jury is still out about whether this is truly representative of the abundance pattern for gas giants in general. And lo and behold, this prompted many, many other efforts to measure atmospheric metallicity for other gas giants. And I'm showing a summary of those here from a recent review paper by Niku Madhusudan. And you can see that indeed it was premature to say that exoplanets match the trends seen in the solar system. So you can see hopefully a thick gray line showing the solar system power law, and then this whole jumble of scattered exoplanets. And so if, as I said before, if there's anything you take away from this talk, it's that diversity should be expected for exoplanets. It is very puzzling why all of these planets are showing lower than expected water abundances. It could be something that we don't understand yet about planet formation. We think that water is one of the most fundamental building blocks of how planets form, and that most atmospheres should be highly enriched by infalling planetesimals that are rich in water. Perhaps there's something wrong with that picture. Perhaps there's something we don't understand yet about the atmospheric chemistry. Now, it's very early days still, and I think we need more and better data to robustly say how much of the scatter is real and how much of it is because the information we have at the present moment is limited. So fortunately, we have a lot of really great data that are new and coming soon. A couple of the facilities that I'm most excited about, here's a beautiful spectrum from Gravity, which was designed to look at the galactic center, but turns out to be great at measuring spectra for exoplanets as well. This is the spectrum of Beta Pictoris b, showing a substellar carbon to oxygen ratio for the planet that is indicative of a lot of enrichment in water by accreting planetesimals. There are also high spectral resolution observations from the ground, and this is a just absolute blockbuster result showing a detection of 6 different molecules in the atmosphere of HT 209458b, the first detected transiting hot Jupiter. And this is so recent, we're all still scratching our heads about what this means, because for normal chemistry, you would not expect all of these different molecules to be present all at once. So perhaps what we're seeing is some 3D effects that were during a transit of the planet. You see the eastern limb and the western limb. They have different temperatures, different properties. And so I think this is just a teeny tiny preview of how complicated exoplanet atmospheres will turn out to be as our data continue to improve. We're also very, very excited for the upcoming launch of JWST. Here's a simulated spectrum of a hot Jupiter from an approved early release science program from the Transiting Exoplanet community. With JWST, we'll get complete spectral coverage between roughly 1 and 5 microns, and extending all the way to 12 microns with MIRI. And with data like this, you can very easily detect features from a lot of different absorbing species in the atmosphere, so water, carbon dioxide, CO, methane, depending on the temperature, you could see ammonia. And the hope and expectation for data like this is that we will be able to measure the metallicity and elemental abundances for these atmospheres at a level of precision that is on par with what has been achieved for the solar system planets. And finally, later in the 2020s, we have the launch of Ariel coming up, and this will be the first dedicated atmosphere characterization mission that will measure spectra of a sample of about 1,000 exoplanets. And I think this is really important because as we're seeing, planetary atmospheres are extremely complicated. I was asked once by a very eminent cosmologist whether I expected that we would have a grand unified theory of exoplanet atmospheres. And I said, not anytime soon, because as Martin said in his talk earlier, planetary atmospheres and biology and life are a lot more complicated than you can describe with just 6 parameters. Okay, so I'd like to talk a little bit about clouds as well. We know that all solar system planets that have substantial atmospheres also have clouds, and we're interested in whether they are also present in the atmospheres of exoplanets. The telltale signature of a cloudy spectrum is that the clouds will truncate the spectral features because the light from the star cannot pass through an opaque gray cloud deck. So we've already seen definitive evidence for clouds on a number of exoplanets. This is maybe my most infamous result. It's a detection of clouds on a sub-Neptune. This is a roughly 2.5 Earth radius planet, about 500 Kelvin. These planets are really, really common outcome of planet formation. And everyone and their mother was trying to measure the spectrum of this planet. It orbits a nearby star, so it's one of those benchmark targets that's as easy as could possibly be to observe. But all of the observations were inconclusive. You could flatten the spectrum by putting clouds there. You could increase the metallicity of the atmosphere, and that will also shrink your scale height and shrink the amplitude of spectral features. And so I and my collaborators measured a record 15 transits of the planet with Hubble, and found that the spectrum is flat as a pancake, so flat, in fact, that all plausible high mean molecular weight compositions are ruled out. And so clouds or haze must be present in the atmosphere.
5 minutes.
Thank you. So the clouds have to be a lot different from clouds on Earth. They have to be much lower pressure, below about 1/10 of a millibar. At the temperatures on this planet, you could expect equilibrium condensation of salts and sulfides. So this would be clouds made out of zinc sulfide or potassium chloride. You can also get photochemical hazes from methane photolysis. Everyone asks me what color the planets are. This is something that we actually haven't been able to measure yet. But here's some model spectra for this planet that are convolved with the human eye response. The two different rows show what the planet would look like being illuminated by its red dwarf host star on the top versus the sun on the bottom. And I have to say, I was kind of disappointed by how ugly all of these colors are. So maybe these aren't actually right. And when we go measure an albedo spectrum, maybe it'll be a little bit less of a like sewage green color, I hope. And of course, we have found that not all sub-Neptunes have insurmountable clouds. There's some tentative evidence emerging that hotter planets tend to have less cloudy atmospheres. Very recent exciting result is that if you push to the coolest atmospheres, you may start to see the clouds and haze dissipate as well, or maybe sink below, condense out below the part of the atmosphere that we're observing. So this is a very, very interesting result, a detection of large features in the spectrum of a habitable zone sub-Neptune planet, K2-18b. This planet has a substantial amount of hydrogen in its atmosphere, so it's not considered habitable, at least not in the conventional sense. But it is very encouraging to start exploring the atmospheric chemistry at these temperatures to see that for a 250 Kelvin planet, we can clearly see what its atmosphere is made out of. So I think this bodes well for pushing to characterize the atmospheres of true Earth analogs. So in my last couple minutes, I'd like to talk about what we know about terrestrial exoplanets, and in particular, the 0th order question, how often they maintain atmospheres at all. So we talk a lot about biosignatures, that's later down the road. My first question is there an atmosphere there at all? And there is reason to believe that the solar system terrestrial planets are not representative of the overall terrestrial planet population in the galaxy. Most rocky planets orbit M-dwarf stars that are smaller than the sun. This is kind of a blessing and a curse because it's easier to characterize small planets around smaller stars, but their atmospheres are endangered by higher levels of UV flux. Many of the planets are expected to be tidally locked, so you can have the atmosphere freeze out and collapse on the night side of the planet. So these are some red flags. We don't know yet how often atmospheres are able to survive in these circumstances, but we're starting now to be able to characterize the atmospheres directly and find out. So the current data rule out light, fluffy, hydrogen-rich atmospheres for these planets. That matches theoretical expectations for what they should look like. But high mean molecular weight atmospheres or clouds are still possible, or there may be no atmospheres at all. We do have one trick that we can use to tell if an atmosphere is present. And this is to measure a thermal phase curve. So the idea here is that as the planet moves through its orbit, if it's tidally locked, we see different faces of the planet over time. So here the planet is eclipsed, and now the hot day side rotates out of view. And the thicker the atmosphere is, the better it is at redistributing heat from the day side to the night side. And so we expect that a planet with no atmosphere would have a maximum phase variation between the day side and the night side. And very excitingly, TESS discovered a terrestrial exoplanet that was accessible for this type of observation. It has a nearby small M dwarf host. The planet is about 30% larger than the Earth. And the temperature of the planet is 1,000 Kelvin. So that is hot. It's way too hot to be habitable, but not so hot that the atmosphere would necessarily be lost. So this planet was discovered. I got really excited. I stayed up all night and wrote a DDT proposal for Spitzer. Fortunately, in the last 6 months, that Spitzer was still operating. And here is our spectrum. So, or sorry, not our spectrum, our phase curve. And let me tell you, I printed this out as soon as I reduced the data, and I was waving it around in the corridor back when we were all still at work. And I knew from looking at it that there's no way this planet could have an atmosphere. We had maximum temperature contrast between the day side and the night side. We did our homework to check really carefully. We found that regardless of the atmospheric composition, surface pressures greater than 10 bars are confidently ruled out. Less massive atmospheres than that are unstable to erosion by stellar wind. And so most likely what we're looking at is thermal emission from the bare surface of a rocky exoplanet. And with data like this, we can start to ask, what kind of rock are we looking at? And in our case, the surface is so dark that the best fit compositions are basaltic in nature, similar to the lunar mare or the surface of Mercury that you can get from cooling lava on the surface. Okay, so I'm wrapping up. JWST will be able to make similar measurements for a much bigger sample of planets. If atmospheres are present, we will be able to detect spectral features from the atmosphere to reveal the dominant chemical species. So we'll make a lot of progress, but we still will not be able to address whether biosignatures are present in the atmosphere. We'll be able to do the 0th order question, is there an atmosphere? Maybe if there is, we'll do the 1st order question, what are the dominant chemical species? But to search for biosignatures in the atmosphere of a large sample of Earth-like planets, we will need a next generation space mission. And there are a couple of these under consideration by ESA and by NASA. And I would really, really like to see a mission like this launch. Ideally within 20 years. I liked Martin's optimistic viewpoint of when this might happen, but I think realistically, you know, within my career, that's when this will be happening. So the future of exoplanet atmosphere characterization is very bright. There's a lot of exciting work right now and a lot of wonderful work to look forward to. So thank you very much. And if there's still time, I'm happy to take a couple questions.
Thank you, Laura. That was a very clear talk. We don't have much time, but we can do one short question, Mark.
Okay, let me look. So we have several, but for example, one from Michelle Boyce. Maybe I missed it, or am I missing something there? But how does one determine if clouds exist? Is it through some kind of empirical meteorological laws, or is it more naive than that?
We can tell by looking at the spectrum. So if a cloud is present, it tends to block transmission of stellar flux through the atmosphere. And so it shrinks the size of the features that you can see. It's a good question.
Thank you. I think we're copying the questions into the Slack, right? So Laura, you can also go to Slack to the general, to the plenaries channel and there answer other questions if you have time. That'd be great.
I will send them to Laura.
Oh, great. Thank you.
Thank you. Sorry for talking so long.
That was great, was worth it. Thank you, Laura. So our next speaker also has very exciting things to talk about. And I'm honored to introduce him. It's Ben Stappers. Ben did his PhD in Australia at the ANU in 1998. After that, he went to the Netherlands, first for a postdoctoral fellowship in Amsterdam, and then he became a senior scientist at Astron. After that, he moved to Manchester, where he had an ERC advanced grant, still has it actually, and he's there professor at the Jodrell Bank Center for Astrophysics. Ben is interested in radio pulsars, neutron stars, and rapid radio transients. He also is very interested in the development of hardware and software that you need to analyze these phenomena. He's one of the co-discoverers of the extragalactic nature of fast radio bursts. He's a member of the European Pulsar Timing Array and the International Pulsar Timing Array projects. He's PI of the Meertrap Search for Pulsars and Fast Transients and co-PI of the Transients Key Science projects of the LOFAR and SKA telescopes. And today he's going to talk to us about the exciting recent developments in the field of fast radio bursts. Ben.
Thanks very much for the very kind and generous introduction. Yeah, it's an absolute pleasure for me to be able to give this talk today. I really appreciate this chance to talk about this exciting and growing field. And I must start with an apology because there's no way that I'll be able to cover all of the exciting and interesting aspects of this field in the time I have available. So I apologize if I miss your favorite result or your favorite telescope. So the story begins in 2007 when analysis was being undertaken, a reanalysis of data taken with the Parkes radio telescope to try and find radio pulsars in the small Magellanic Clouds. It had become apparent that it was an efficient and effective way to find pulsars apart from using what had become the standard method for finding pulsars of using a fast Fourier transform, was to try and look for single bright bursts or even a few bright bursts of radio emission from pulsars. And this could potentially reveal the location of sources that emitted less frequently or less regularly than the normal pulsar population. These are the so-called RRAPs. And as part of that survey, Duncan Lorimer and his collaborators were reprocessing the data from the Magellanic Clouds, and they found this bright single burst of radio emission. And you can see in the right-hand side a graphic showing time on the x-axis and then frequency on the y-axis, showing you a characteristic dispersion delay associated with a burst which has come from outside of the Earth's atmosphere and has traversed through the interstellar medium. However, there was something particularly odd about this burst, and that was that this delay was significantly larger than could be expected, given what we understood to be the number of electrons along the line of sight. So for example, using our knowledge about the distribution of pulsars and H2 regions and other sources in our galaxy, we're able to make a map of the electron distribution that we would expect. And when you take that map and you place the Magellanic Clouds on it and you look to see what you would expect from both our galaxy and the Magellanic Clouds, you find that you fall well short of the predicted number of electrons along the line of sight that could give you this observed dispersion delay. And so this suggested that this object was actually, in fact, very, very far away, or that the object which generated the burst was, in fact, very, very far away and was actually extragalactic, because, of course, if we're relying on the free electrons in our in the intergalactic medium to provide the delay that we observe, then we need to go over a much larger distance because, of course, the density is much lower than it is within the galaxies themselves. And so it was established that we have this really bright burst of radio emission that lasted just a few milliseconds, happening at large distances, and hence where we later came up with an idea of the name of fast radio bursts. For a long time, this was known as the Lorimer burst because, as you'll shortly hear, there was a long period after 2007 when these bursts were not seen in any other data. So what do I mean by saying that the dispersion was too large means it's extragalactic? Well, if you take the this region on the far right-hand side as being the approximately the distribution of electrons in our Milky Way, and then you place a source of burst of radio emission at the center of the host galaxy where it might have occurred, for a burst where we've measured, say, a so-called dispersion measure, which is a measure of that delay of something of the order of around about 1,000, then we would predict that if it was in the center, we might expect about 700 units of this DM to be from the host galaxy. We'd also expect a contribution from the Milky Way. And in that scenario, we'd expect that the distance to the source might be something like 2.2 gigaparsecs or a redshift of around 0.6. However, if the source was at the edge of the host galaxy, for example, then there'd be much less contribution from the host, and we might expect the redshift to be actually greater. But already we're starting to see that these objects with these large measures of large dispersion measures are at redshifts that are significant and potentially cosmological. It's also the case that we don't really know what lies in between. And so these objects provide us an opportunity to probe that, and I'll come back to that later. As I hinted at, this object was discovered in 2007 in data taken in 2001. And it wasn't until 2013 when the High Time Resolution Universe Survey was looking at its data, and a student in Manchester, Dan Thornton, took a look at for these bursts because everybody was super keen to see if there were more of them, and thus establish whether there was a real population of so-called fast radio bursts. And he was lucky enough to find 4 more of these bursts in that data set, thereby establishing these objects as being a distinct population. And they were all located at large distances, and they all exhibit a dispersion relation. In this case, you'll hear later on how things have become more complicated, but in this case, the dispersion relation was exactly what we'd expect for a 1 / frequency squared relationship. And you can also see that these bursts exhibit scattering, which is also attributable to the medium along the line of sight. So we've now established that there was a population, and as of just about 3 or 4 weeks ago, the published sky of fast radio bursts looked something like this. So you can see here, the white dots represent the known pulsars, just for comparison, and the background color scaling corresponds to the expected galactic contribution to the dispersion measure, whereas the dots themselves, the color, corresponds to their actual measured dispersion measure. And you can see that there's a large population of these objects, and they are distributed all over the sky, and they've been found by a whole range of different radio telescopes by now, ranging from the Utmost telescope in Australia through to Arecibo and ASCAP, for example. So we now have this extragalactic population of sources, a few dozen of them as of a few weeks ago, to take a look at and understand what this population is telling us. This early population that was discovered with mainly the Parkes telescope were only ever seen once. They were only seen to show these bursts, these few millisecond long dispersed radio bursts, were only ever seen once. Many dozens to hundreds of hours of observing time were spent trying to see whether they burst again. And it was only with the discovery and then subsequent observations of the fast radio burst 121102, which was discovered with Arecibo, that we got a bit of a surprise. And that is this corresponds to the first repeating burst. So bursts were seen on more than one occasion. They were detected at many frequencies. It was certainly observed even early on that these bursts came in groups, so that the bursts themselves had a bursty nature. And they had something that was a bit strange compared to the other bursts that had been seen to that at that stage, is that they had weird spectra. So if you look at the intensity as a function of observing frequency, you found that they often had very variable spectral indices. So they might have a negative spectral index for one pulse, and then the following pulse that was detected might have a positive spectral index. Or as you can see in later observations on the far right-hand side here, they actually have a much more complicated structure. They exhibit features which seem to defy the dispersion relationship, or deviate, I should say, from the dispersion relationship. In all of the pulses that are shown here, we've tried to optimize for the shape of the curve. And so this, where it's straight, is what we think is the most likely value for the dispersion measure. But you can see that there are variations and deviations from that. In the presentation earlier by Lord Rees, he mentioned about potential links to neutron stars and the results of, or the predictions of Zwicky. And so indeed, when this first repeater was identified, it was recognized that there was a possibility that we might be able to actually measure the period of this source. So if there was an underlying rotational period, then that might be possible. To date, that still hasn't been possible for this burst, nor for, as far as I'm aware, any other fast radio bursts. And there are many hundreds of bursts now seen from this object with many different radio telescopes, including the FAST telescope in China. So one of the advantages that you get of having a repeating source is that you can put all your ducks in a row, as it were, to be able to do a follow-up observation to try and localize the source. Up until a couple of years ago, all of these fast radio bursts was found with single dish telescopes, which basically had relatively poor spatial resolution, which meant it was very difficult to be certain about where they occurred if you were trying to localize them in a host galaxy. So with 121102, if you were lucky and you were pointing your interferometer, in this case the VLA, and then subsequently the EVN and eMerlin, at the source at the right time when it gave off a burst, then it would be possible to use imaging techniques to actually localize the source in the sky. And this was done for 121102, and surprisingly, the host galaxy properties were really not what people might have predicted. It was a dwarf galaxy. It was located at a redshift of around about 0.193, which fitted very well with the expectations from the understanding of the distribution of electrons in the intergalactic medium. The mass was around about 10 to the 8 solar masses. It was concluded at the time of the discovery that this host was consistent with the hosts of long gamma ray bursts and luminous supernovae, for example. You'll also notice that the fast radio burst given by the red cross in the middle panel there is located near a knot seen in the HST filters, which suggests a region of potentially star formation going on. So after the discovery of 121102, of course, people were very keen to see if there were more repeaters. And CHIME, which is a telescope and experiment running in Canada, which I'll come back to a little bit later to give you a bit more detail about, has been scanning the skies for a few years now, and they've discovered more than a couple of dozen more of these repeating fast radio bursts. In the vast majority of cases, they've detected these particular sources to burst less than a handful of times each. They're seen to burst, have a range of different dispersion measures, suggesting they're all at a range of different distances. Their widths seem to show that they may be different from those bursts that we've only seen once so far. And I'll come back to that a little bit later on again as well. And as I already touched on, the repeaters allow for localizations because you can plan follow-up. An interesting aspect of this repeater source idea and the follow-up of repeaters is that a burst detected with the ASCAP telescope in Australia, which is an interferometer which has found a large sample of fast radio bursts. They'd spent an enormous amount of observing time looking with both ASCAP and then the Parkes radio telescope in Australia to see if they could detect another burst from one of their sources. And it was only when they looked at it with the Greenbank telescope, which had improved sensitivity, that they found a burst around about 600 times fainter than the initial pulse that was seen. And so this suggests that these bursts may exhibit a wide range of different luminosities. A lot of people have tried to look into the idea of whether the population that we know about is consistent with all of the bursts, even those that we've only seen happen once, being repeaters. And we did some work on this ourselves, but you can also see at the bottom there a list of other references which reached similar conclusions. And basically what we were able to say is that we could not rule out that all of the fast radio bursts came from one population, even allowing for the longest follow-up of the longest follow-up observations. And so why is this important? Well, it'll become important a little bit later if we want to think about whether there is one mechanism by which you can generate these bursts, or perhaps whether there are multiple mechanisms. We're just going to touch on a few more of the interesting localizations that have happened of bursts now. This particular burst, and I apologize that I'll be changing between different naming conventions for these bursts. Recently, we've converged on a new naming convention, and so sometimes I still call the bursts by their old names. But there was a burst detected with the CHIME telescope with the name FRB 2018-0916b, and it's a repeating FRB. It was only the second repeating FRB to be localized, and it's localized to a star-forming region. You can see in the left-hand plot there, which shows a spiral galaxy. The redshift in this case is 0.03. And the localization used the European VLBI network. In this case, there's no luminous persistent radio counterpart, whereas FRB 121102 has a very bright radio source localized at the same position as the fast radio burst. The host in this case, the host galaxy, is radically different. As you can see, it's clearly a spiral galaxy before we had a dwarf galaxy. And it contains over 100 times more stellar mass and has a metallicity 5 times higher than the dwarf galaxy we saw for FRB 121102. So the difference suggests that not all FRBs can be tied to the types of objects or galaxies that host long GRBs and hydrogen-poor superluminous supernovae. So again, the picture's now getting a little bit less clear. One of the favored models for FRB 121102, plus a lot of other FRBs, as we'll come back to shortly, is that they could be highly magnetized neutron stars, so-called magnetars. And the model for FRB 121102 is that it could be a young and rapidly rotating magnetar, pretty much just born. In this case, if this was to be true for this object, the authors of this paper argued that it meant that it would have to be a lot older than the 121102 source. A radical change happened in the field when ASCAP came along, which is, as I mentioned, is an Australian SKA precursor telescope, and it is an interferometer. They do their searching using what we call an incoherent beam, but because they have the capability to store the data from the individual dishes, they are actually able to localize one-off bursts. So when a burst happens, they're able to trigger their system to be able to record the data and then go back and make an image and therefore localize the source. And so that's really changed the field, and they have achieved sub-arcsecond localization of a burst. And in this case, they've actually been able to show that the burst passes through the halo of a foreground active galaxy. And so they're able to use that as a probe, effectively, like shining a torch in the darkness through this galaxy to work out some of the properties of the galaxy through which the fast radio burst has traveled. The number of associations is growing. So here is a rogues gallery of the localizations that have been achieved. The vast majority of them are associated with the ASCAP telescope, but you can also see some from the VLA and also the DSA telescope. And so there's a whole range of different host galaxies are being identified from where we're seeing these fast radio bursts. So this growing sample of localizations means that we're able to start to look at these properties and see if there's any commonality or any distinctions that can be made. So there's around about 15 host galaxies confirmed so far, with redshifts in the range of 0 to 0.66. The host galaxy of the 2020 1124A, for example, than the non-repeaters are more massive and tend to have an older stellar population than the first repeater, 121102. So what makes that one stand out?
5 minutes.
Thank you. So FRB's 2019-060-8B, which is a non-repeater, and 0916B, which is a repeater, have similar locations in their spiral galaxies. Again, when I say repeater and non-repeater, of course, I am saying at the present moment, because of course it is possible that these sources may ultimately be detected to repeat. And the physical offsets from the centers of these galaxies range from somewhere from around about 0.6 to 11 kiloparsecs. And I give a clue to what's coming on the next slide by saying not including M81. And the offsets are consistent, as long as we're not referring to 121102, with short GRBs, in fact, now, core collapse, or even type 1a supernovae, and tend to disfavor the long GRBs. So again, is there a hint here that perhaps there's more than one mechanism generating these fast radio bursts? However, magnetars formed via a number of different channels, and not necessarily all of them being formed in the same way, but all of them ultimately ending up being highly magnetized neutron stars, could be consistent with this population. A really recent interesting result, which is again throwing another spanner in the works, as it were, of our understanding of these systems, is the repeating FRB that was detected in M81. So the burst was the source that was originally detected by CHIME. It was shown to be a repeating fast radio burst, and they discovered that the dispersion measure was now just 87, which is only around about twice what you would expect from our own galaxy. And they were able to use CHIME to do an initial localization region, and they compared it to the optical and H1 extent of the galaxy, and you can see that it lies in the outer reaches of the galaxy in the H1 gas region. Subsequent localization by the PRECISE project using EVN has placed it in the black region that you can see in the center of this plot, which lies right on top of the globular cluster known to be associated with M81. So suddenly we've got another a variable in the system, and the authors argue that the source cannot be a magnetar from a core collapse supernova, and favors highly magnetized neutron star, a young neutron star formed through accretion-induced collapse of, say, a white dwarf or a compact star merger. So I'm just going to skip over a small section there in light of time. One other thing a few other things I just wanted to quickly highlight is that I mentioned that we don't have any idea about rotation periods in these systems. However, we have noted in 2 of the repeaters that there are periodicities. And these periodicities are to do with the underlying burst distribution. And we find that the bursts in 2 FRBs tend to be concentrated in certain regions in time, and those periods of time repeat. So for example, the burst 1809-16 repeats with a structure of around about every 16 days, whereas 1211-02 repeats every 160 days or so. And these favor models which maybe you have a high mass X-ray binary, but there are other proposals such as planets, ultraluminous X-ray binaries, accreting binaries, and a so-called binary cone model. I mentioned a few telescopes already. There are a huge number of telescopes around the world being used for looking for fast radio bursts and for their follow-up study. And I just don't have time to go into them, unfortunately. But the big news in the last few days, and I would certainly refer you to Emily Petrov's talk later today for much more detail on this, is that the CHIME telescope, which has managed to find many hundreds of FRBs and probably thousands by now, using a combination of sensitivity and wide field of view to really deep down probe the population. And just to give you an idea of the CHIME sample, here's the graph I showed you earlier. And now if I superimpose on that the CHIME sample, you can see how radically they've revolutionized the field with their announcement of 400 or so new FRBs that they've recently found. And what has this told us about the population? Well, they find that the repeaters and the non-repeaters definitely differ in their spectral properties. They show that the log n log s seems to be consistent with a Euclidean distribution. They find that the rate is of the order of around about 1,000 bursts per sky per day, or above around about 5 Jansky milliseconds. So just to skip forward a little to the cosmological probes. So fast radio bursts have this potential because of their large distance to be detected out to very large redshifts, and therefore we can use them as cosmological probes to look at things like the epoch of reionization of helium, for example, but also we can do the search for the missing baryons. And I refer you to the paper by McQuart et al. From last year, where they've shown with a sample of localized bursts, a result that's consistent with the expected baryon density. So in the last second, I just wanted to show you a highlight from our own work. The MEERTRAP project, which is using MEERKAT, which is an interferometer, also an SKA precursor telescope, where we've managed to find and are starting to localize fast radio bursts, and are currently pursuing optical follow-up of those bursts. So just in terms of time, I'm just going to stop with a bunch of where next type questions for this infant field, which potentially has impact on a large range of different areas of astronomy. Thank you.
Thank you, Ben. That was a very good talk. Thanks. I don't see any questions, and I think in view of time, we better leave the questions that may still come in now to Slack, because we don't want to want you to be late for the parallel sessions that are going to start in less than a minute. So let me just close by thanking all our speakers in this session, and wishing you lots of more scientific fun for the rest of the afternoon and the rest of the week. Thank you to everyone, and particularly to Ben.